So I'll kind of give an overview of the idea of what are creative applications of machine learning, and then the question of evaluation of these applications. Kind of adapted some slides from previous talks. Kind of the question in general of what is creative computing, what are creative machines, I think is in general a very timely question, right? So I don't know how many of you have seen this picture. I know there was some people, there was also a class on deep neural networks for arts that was offered, which was more visual. And I think it was an ACE, so I don't know if anybody's looked into creative applications of in the visual domain. So if this is the first time you see this picture, and you can see the signature of the artist is actually, I hope by now we recognize that this is a min-max, right? The loss functions for again. This is actually a picture that was sold at Christie's for $432,000. Kind of brought up this question. I mean, like, how do you value art that is made by a machine? Why somebody is willing to pay such a big amount for something that was actually an outcome or output of a piece of code? And of course, it kind of went to way beyond the amount that whoever, and I mean, people who actually created this drawing didn't expect anything even close to this. Even more surprising was that this was not even their code. I mean, they used the code by this guy, Robbie Barrett, who published some of his adaptations or applications of GANs for visual arts. And once it was sold, they actually kind of came up with this tweet about the fact that this was like a work he did a year before that, and that he created all of these additional images that were basically done for free. And now suddenly there is somebody else who is selling his results. Of course, it was kind of printed on a high-end canvas and put in an expensive frame, but still, paying hundreds of thousands of dollars for something that you can generate at the click of the machine. So actually, the group that did that was 3 French students who have this sort of a artistic group that does computer-generated art, and they basically not only used this code, they actually consulted with him. He helped them to get this code running, and then they went and put this in the museum. And then the question was, it's just a provocation or a joke, but they actually made this money, and why somebody would pay for this. But this whole anecdotal story is really related to the question of why would somebody go and assign such a value to the art, to computer-generated art. Does that mean that this is valuable? So he generated a lot of portraits, and in some sense, it's kind of an abstract way for the machine to see the world and then recreate this in its own impression. So I'll kind of a little bit talk more about the idea that a creative machine somehow captures something about the world in a way that might simulate human level of creativity. So why we would study creative machines, one is to better understand the human creativity, also formulate algorithmic perspective on creative behavior in humans, and eventually kind of create some synergy so the humans and the machines can work together and hopefully enhance the human creativity without the machine necessarily being totally creative. And this is an important point that I would like kind of to emphasize, is that even if the first question is more cognitive science oriented, and there are actually conferences and research going into the questions of human creativity from psychology aspects or science aspects, and of course interactions with computers. And part of this research also tries to formalize this in kind of an algorithmic way. The third part is really the practical one, at least from my perspective, is that we live in this sort of a very computer embedded world where content is generated by the machine. And it doesn't mean that we totally, submit to the machine. I think the question of how to be more efficient and effective with the machine together, and how you specify your instructions, your desires, your intent to the machine, so that things will emerge together in some kind of a more efficient and creative way. And again, I think outside of experimental art, anything which is like virtual reality, extended reality, computer games, I think that's where these things become much more evident, because the machine generates realities for us, but they have to be in some way responsive and maybe correspond to some other human design. From a very high endpoint, I think this is also very much related to the question of creativity versus computation, or in the evolution. So this is a photo I took from the Museum of Anthropology in Mexico City, and they opened the museum by surveying the history of arts and historical anthropology kind of timeline, and speaking about creative revolution. And the kind of the idea here, it's a long text, so I'll kind of try to summarize, maybe read parts of it, was that there was a big change, or something happened between so-called Homo erectus to Homo sapiens. Now, Homo erectus, from many aspects, was very similar to Homo sapiens. And one thing that was evident from the archaeological excavations was that Homo erectus was making tools. I mean, he was a skillful hand axe maker. He had different things that he could actually use for survival in the prehistoric world. But the thing is that he basically used the tools for a specific purpose, and it didn't extend to something that happened once the Homo sapiens started, like that kind of creative revolution step. So the idea was that the Homo sapiens suddenly developed many more tools, and these tools were not only much more diverse. The point was, and this is kind of the last sentence here, is that Homo sapiens developed different tools for specific purposes, such as bone needles, as well as elaborated decorative objects that were not directly related to survival activities. This marked the great difference. So something happened that suddenly the early humans not only could make tools, not only that, because a lot of the intelligence is kind of attributed to the idea that we as humans can make tools, but also many animals kind of use objects as tools. And then, what the next paragraph says is that really the idea of creating unnecessary tools, in some sense, objects that are not directly related to survival. So the objective function is not necessarily optimizing your hunting abilities or your, ability to make clothes and keep warm, or or you know, create a place to refuge and live there. But the thing that emerged, and I'll kind of read this in the last half year, is that the real revolution was not as much a technological one as was a change in the creative ability reflected in art and in the conception of magic, mythic, and religious universe. We don't know the exact moment in which this radical change took place due to the perishable nature of the materials. Treatment given to the deceased by means of burials, fabrication of decorative objects, and cave art paintings are the proof that whoever made them were essentially the same as us. So something happened that people started looking into questions of beauty, of imagination, maybe prejudice, maybe magic and myth, and started creating things which could not be directly related to their survival purpose. So why is that? Why would the system start generating more than it actually needs for performing specific tasks? So of course, the creative technology, at least the idea of the ability of intelligence, artificial intelligence, is the kind of considered the fourth industrial revolution, right? And the AI and neural networks takes big part of this, and of course, big data. Now, a big revolution in neural networks actually happened with the idea of generative neural networks. So if you have Hinton and Ruslan Sadolnikov, who came up with these early restricted Boltzmann machines and modeling things in these generative ways that we kind of mentioned, the variational models, basically modeling the probability that would generate more and more stuff. That was kind of a big change after a long history of neural networks that started from basically the McAuliffe and Pitts early neurons, and then the perceptron and the Minsky and Pepper, to kind of killed a lot of this development by showing that the very simple perceptrons could not solve issues like the XOR problem, the linear aspect. And so it took a long time, this dark age of neural networks, until the the backpropagation, multi-layers re-emerged, and again, the classical support vector machine, I think, was the big time of the the 90s, and then the beginning of the millennium, only until the generative abilities of neural networks came again. So why do we need to think about the ability to generate something? And if we assume that generating something is a creative process, so from more of a psychological perspective, Margaret Bowden published several books which became kind of landmarks also for the computational creativity community, and we're kind of trying to see what does it mean that something human or a machine is creative. So on one, the basic aspect is that you can have either your personal creativity, the peak creativity, or edge for historical creativity, but that means more like some creativity that changes changes something for the humanity in some sense. While personal could be that you yourself are you're doing something creating for yourself. It doesn't mean that there is a novelty that will change the way the world operates. But in general, it's the ability to come up with ideas and artifacts that are original and valuable. So there are two things here. Something that is original in the sense that, something exactly that this wasn't done before. And there's also the question of value. So what does it mean valuable? And we'll kind of talk about this aspect a little bit. Now, if something is creative, it doesn't mean that it's created to the same extent as anything else. So the three levels that she suggests is, one is exploratory creativity, which is maybe what most naturally the neural networks that we're looking at do. You basically have a set of possibilities because you model an information source, you have some kind of representation. And by moving through some space of parameters, you generate more examples. You explore an existing space, and every time you get to a point that somebody else hasn't visited yet, you interpolate something, you move outside of that cluster. And we have seen these examples, right? And Ross was showing examples with MNIST, and we kind of mentioned that same ideas could be done maybe in audio or musical domain. Once you define some kind of a space, now you can start generating examples which are new. Maybe not totally new because they kind of blend and provide abilities to interpolate between existing examples, but it's still creative, it's still new and novel, and of course useful. So originality and valuable still applies to these things. Another example is what Bodden calls combinatorial, but the idea of combinatorial is not mathematical combinatorics. It's the idea that you combine two different domains and you create a new source. So doing style mixing, which is something that artists have been exploring and have done some work in this domain also, is if you model two different domains of music, two different genres, interpolating is a combinatorial. We spoke about interpolating within the same musical style, so within the same domain, moving in latent space that makes more sense than interpolating on the data. But you can also think about so if one is interpolation, the other one is extrapolation, or interpolating between separate domains. So these are also kind of, at least conceptually, pretty evident. And the last one, which is really the hard one, and that's kind of the ultimate creativity that we might be seeking, and maybe this is where humans are, different from the machine, is transformational creativity. Transformational means that you come up with totally new understanding of the world. You change the concepts. So I don't know if you're going from classical physics to quantum physics, or some other theory that totally changes our understanding of how things operate. And that means we kind of redo all of our models in some surprising way. I think this one is, in some sense, ill-defined, or at least for me, I think this is really hard question of how you would really become creative. How do you come up with a new genre, which is not just interpolation of existing genres? How do you kind of redefine your worldview by kind of coming up with something totally novel? So the process of creativity, people were exploring these questions from psychology perspective, and Donald Campbell, who's a psychologist around 1960s, proposed this mental process that he called BVSR, which combines so-called blind variation and selective attention. And the idea is that the first part is really generating more and more examples. So if you explore a space and you create these blind variations of an idea, this is from Picasso's Guernica sketches. He was exploring, the concept of a bull, right? And different ways of representing this. But eventually you want to put it together into a piece. So you need to provide some sort of constraints. So the naive way for me to kind of next to connect this with what we are doing would be, yes, if you have a generative model that can do the blind variation, which means you kind of bang your random number generator and get more and more instances of maybe some abstract idea. And these are the realizations of possible variations. Eventually, you need to present some sort of meta specification, some kind of a control signal that will run this kind of a random process. It's very structured, but it's still random variations. They're blind, and now you will guide it into some sort of a overall composition. So this is where I think the query, the ability to control and query the generative model comes in, at least kind of the most naive way of translating this psychological principle of BVSR to some system design. Now, you know, just observing the way you know, Picasso was working on these different sketches, you can see that it can go from, you know, very detailed and realistic representation of a bull to something which is very abstract. So I think that kind of just suggesting that you know, the compression part is kind of a tool of thinking, at least for Picasso. So we spoke about some breakthroughs in machine learning, like the representation learnings that you can have an encoder, have a latent attributes, and this list can be detailed enough, and the mapping can be encoder to coder sophisticated enough to reconstruct the image, and that's really one of the breakthroughs that you know, we covered, and I think this is kind of in this creative review today. I kind of want to point some of the aspects that we already discussed, so we can see them in this context. So representation learning is really essential to be able to kind of have this sort of abstract or condensed view of a problem that then can be rendered in different ways. We spoke about the generative adversarial networks, that this is the slide we have already seen. And we spoke also about the idea that the information source is basically represented as a probability distribution. And if we sample long enough from that source, we actually extract only some subset, the typical sequences, the phrases, things that actually capture the global structure, and you know, the entropy and the compression is one way of coming up with this representation, this official coding book. So you can extract information by encoding. So you take your data, turn it into some kind of a code, either compression code, latent code, and then you can reproduce the information by sampling or reconstructing somehow the code in interesting ways. So you know, that was a little bit of a motivation, very different, but just the concept itself. You can use machine learning to create these code books, and that could be either style specific, or it can be, of course, much more creative than a fixed set, even though this is a big, you know, exponentially big or combinatorially big amount of possible compositions. But think about this as a model, as a language model. And you know, today with the GDCs and language models, actually in the text domain, there are amazing results. So here's an example of kind of a style mixing. So the second idea, where you can basically interpolate between or combinatorial in the sense that Margaret Bolton spoke about combining two styles. So this was a set of pieces that was kind of created by running through sets of different musical styles, and then rendering them using you know, the factor oracle model, basically, and kind of the reactions that I got, and I kind of quote here a response by Dick Moore, who was our faculty. You know, he passed away a few years ago. He was one of the you know, early fathers of computer music in general, and you know, he referred to this process a little bit of a lucid dream. So this is sort of a process where you as a dreamer become aware of some kind of experience in progress that you might have as a dream, but you kind of like, you're awake and dreaming. So the lucid music touches upon something essential about the musical nature of mind, of intelligence, of consciousness. It's not about producing more violin pieces by past composers. It's a musical tool for exploration of mind, its boundless ability to fail to interpret. So I'll kind of play a short excerpt because this is more of a really classical kind of musical remix done by a machine, but in a very fluid way, I think. So I don't give a little bit of that notion of just make sure I have the audio. Where's my share? Okay, yeah. Am I sharing the same thing now? Let's hope I'm back to this screen. Am I sharing still the same screen? I just activated the audio. Just a quick thumbs up. Yeah, thank you. So here's a quick example of the piece. Just a second. Okay. So kind of every note here was basically, in some sense, recopied from a different musical source. But I mean, the transitions were fluid. I mean, they're basically kind of very much like the continuation in Lentils Eve once you model this across different sources. And then the question is really more about the perception than the technical process. This is another example of the machine improvisation, the variable Markov oracle, a tool that I mentioned, and in the slides we actually have the link to the GitHub. This is a pure data interface to this system, and the graph we spoke about this, what it does. So kind of the idea is that by using this graph, you can think about every new moment in music that reminds something else, the past. And this is kind of a memory graph. And then the computer dreams or hallucinates the future by recombining past memories. And you can control this hallucination by querying this memory graph with another input. So at least in this model, there was a little query mode where you can input a sound, and it will try to navigate this random process of moving on the graph towards the target sound. So kind of the use would be, if you want to end the piece, for instance, you hold the note and then the other improvisation. So you have the musician performing and then the machine is improvising. If you hold a note, you click the query, it will try to navigate its improvisation so it kind of is harmonious with whatever the musician is playing. So these kind of ideas of having a control or a query over music are actually, I think, very important for the ability to do something useful with these generative models. Maybe a short example of well, let me skip. I see that the media is not synced, so I'll skip this. But this example that I tried to play the previous time, I hoped it will work today because I checked it before, but it wasn't through Zoom. We said that we can actually query a song or one musical piece with another musical piece. So as we said, we had an original saxophone recording. So you build a model of this recording. Again, this is not in the big data sense of deep learning that actually creates a very detailed model of a corpus. This is really kind of a one-shot thing that you create on long enough. You do need a long enough recording, but it doesn't have to be huge. And then you query this with a different accompaniment. So this is the part of it that was difficult. I hope it works now, because you'll have the improvisation of the saxophone on one channel and the query on the other channel. So the query is the accompaniment, and then the saxophone is actually recombined. So let's hope it works. That's amazing. Okay, at least to me that you don't hear the saxophone now. Again, I don't know. I'll point to I actually put this as a YouTube link, so we can kind of address this. But kind of the idea was that using this, at least what I could hear was just one of the channels, which is the query. It will generate a new improvisation based on the model of the saxophone. So you'll have this saxophone improvising on this music. Some other works pretty much we kind of inspired by same type of thinking, but very different technologies. One was trying to train basically a variational autoencoder on, this is really done by bar by bar, okay, on a corpus of music. I was using some sonatas by Prokofiev. But then the idea was that you would query. So the model was trained on one corpus, not very distant, but still a different set of pieces. And then you would encode and decode a different musical material through this. So again, I'm kind of exploring here the idea of querying or somehow navigating the latent space. We have seen examples where you can generate more of the hidden space and then decode music. We have seen Chris Donahue's work where this hidden space was 8 buttons, and the decoder was, well, the encoder decoder were trained on a corpus of large corpus of music, and then you would basically generate new pieces by kind of randomly, even though the gestures were kind of mapped in this meaningful way, but you would trigger the hidden space and will decode something. Here the idea was that you actually train the whole encoder decoder on one corpus, and then you then use as an input a different set of musical pieces. And kind of the motivation was that if you encode a different set of musical pieces here, if you use a different set of musical pieces here, they will encode the hidden states in kind of a meaningful way over time, because I was encoding every bar separately. So these hidden states will change in a way that is consistent with the input, but of course they will be decoded in the style of this other piece. So this is kind of a mapping of this input to this output, because the encoder decoder were trained on a piece that kind of hopefully recreates, it's recreated here. I hope it makes sense what I'm explaining. Basically trying to navigate the trajectory of the hidden states by following some kind of a logic or structure that this piece has. So as an example, I mean, this is one of the input pieces. That the beginning would be, I'll play an excerpt in the beginning, which is, so I created several of these pieces and performed them in the concert. The first one is one of the original queries or the original inputs. So we can kind of hear how the query or the input sounds like. just finish this whole piece because I don't want to, I know where exactly to jump. So it will finish and then we'll have this version played. Yeah, so the next one will be basically this map through a AutoEncoder. Yeah, so this is kind of the overall idea of, I mean, whether this is new, I mean, how creative this thing is. I mean, basically it kind of tries to follow the logic, the structure. You can actually see that there are some kind of repetitions in this piece that also reflected here. I mean, this one has a section here that starts repeating itself with some extra materials. You have a transition section. So you do get kind of a similar idea, and then you have the ending, which is kind of a little bit remote from this. So the idea of musical structure, long-term structure, not only in terms of repetitions, but also kind of a design, you know, this kind of a scene-by-scene design, I think is very important for us to create you know, a story, a narrative in music. And this is where you know, some new models that take into account long-term structures, not only kind of just long memory, like memory models, but transformers and structures, I think, become very interesting because they allow you to generate musical forms that have also kind of a short-term or local surface resemblance to some style, but also then they kind of generate something which is long-term. And in this case, you know, I'm kind of using another musical piece to give me the scaffolding or the structure, both harmonically but also in time, because it repeats itself, so it has its own structure to generate a new musical piece. So kind of want to maybe a little conclude by giving some even kind of a higher level motivation from psychology maybe, or well, it's not exactly psychology, it's more like mathematical formulation of some brain ideas. So the concept of the Bayesian brain, which actually you know, was using some ideas of Helmholtz and Bayes, where we kind of want to use some of the concepts we learned also as a possible intuition into how our brain works. So one idea of this free energy minimization, this is exactly the elbow expression that we have seen, which is written slightly in a different way. You can kind of rewrite this variational approach by assuming that, you know, our brain basically in some sense tries to imitate or approximate this is our trial distribution that tries to understand the world by being able to approximate it. Now, having said that, I mean, you know, that sounds very dry and technical, but if you think about this, basically this is where our imagination resides, right? We use our neurons to approximate something that happens in the real world. And as a probability, it can also generate its own variations, right? So something happening in your brain, it can also generate new hallucinations in some sense. So there's this kind of a principle of free energy minimization that some neuroscience researchers like Kristen have been exploring more extensively or intensively. But the idea is that, yes, you try to approximate your real world, okay, by trying to kind of get the maximum likelihood, and you also have this entropy constraint or entropy regularizer, if you wish, that tries kind of to have this ability of that variational part, your imagination, to be as creative as possible. So by doing this free energy minimization, you basically kind of have this little battle between trying to find something that represents the world while still maintaining as much variation as you can in your in your imaginary capacity. Another aspect of Bayesian brain is also the predictive coding, and the idea is that we actually learn by trying to predict best, and this is where kind of the information rate, the idea of trying to maximize the mutual information between your past and your next prediction. So if you're kind of exploring these two ideas, I think the fun idea, or the fun thing that, part of this is the motivation for musical information dynamics, is trying to understand music as something that, listener anticipates the continuations of music. They reduce the uncertainty about the future, and the whole principle of validation and violation of expectations in music, which is something that was, and is still currently being actively explored by music theorists and people who study musical cognition. This is kind of a process that could be formalized as an information theory aspect. But another interesting kind of analogy that I find is this even more overreaching claim that consciousness is a controlled hallucination. So this is an example of a visual rendering, basically again mapping input-output with a network that was trained on dogs. So I hope we can see this. Yeah. So here the idea is that the network was trained to see dogs everywhere, and now when it tries to encode and decode visual scene, you can see that it can kind of hallucinate dogs all over the place. Wherever you have something that kind of triggers a dog reconstruction, you will get a sort of a hallucinating aspect of the visual, basically what you see. So, what is that supposed to represent? Why would somebody want to go and do this experiment? Well, the idea is that the ability of us to perceive the world is, in some senses, the ability to map this to some kind of existing structure in our brain, the generative part, and recreate it. So you cannot, in some sense, see or hear or experience something that you cannot imagine, or so things that you are not, you haven't ever learned, and you have never represented them as structures in your own cognition, they will be actually absent from your consciousness. Or on the other hand, if you are oversensitive to some type of interpretations of your sensory input, like here, kind of trying really to find dogs in everything you see, this is kind of a rendering of such a network. So kind of consciousness as controlled hallucination, I think, is a very interesting aspect that relates to the ability, or the interest in doing these generative mechanisms and applying them to tasks that, again, they're not, they're imaginary, okay, that they're not like survival related in a specific sense, unless you could say, well, maybe the network that was trained on dogs needed that for its survival, so it would try to jump and see everything as dogs, even if there is a little evidence of real dog being there. So in the last couple of slides, just trying to relate things to information theory and the elbow approach or variational encoding. I think this combination is really interesting because we kind of presented them initially as two separate approaches. One coming from compression encoding, another one comes from basically machine learning and kind of the principle of maximum likelihood, or learning a model, probability distribution from the statistical aspect. But you could actually try to see that the elbow, and there are works that kind of try to generalize this. So I kind of giving you an overview of some mathematical results without, expecting anything in terms of like knowing how to derive them, but just trying to show the links and the motivations. So one could say, one could show that the process of learning the lower bound, for the evidence lower bound, is in some sense could be rephrased as I mentioned, the rate distortion trade-off. So basically the idea is that you're trying to encode something as efficiently as you can, while you also have some kind of a distortion constraint because your encoding is not the best. And you can have these rate distortion trade-offs, and you can actually vary, you can generalize the elbow by having some kind of a tunable trade-off between rate and distortion. In the sense that if you're allowing, if you're allowing, let's say, higher rates, you will get, or if you allow less distortion, you will be learning at higher rates, or you can go the other way around and you can learn at lower rates by allowing higher distortion. And you can basically train with tuning this the weight between these two parameters. So you have to kind of redefine your learning criteria. So it's not exactly now defined as elbow, it's a generalized elbow where you actually have to rewrite these two aspects separately, and you can plug in just the weight factor. So kind of the idea is that you can control the rate and distortion, let's say in the encoder decoder, by adding some kind of a noisy channel here. So without going through any of these equations and how it's derived, but you can basically have a lower rate transmission of information even in the encoder decoder. So what does that mean musically? So kind of some experiments, again, very much like the piece I was showing you before, but in this case, it's more of an experiment trying to understand what it means to lower the rate of encoding decoding if you have something which is trained and basically supposed to do well, almost a perfect reconstruction, right? VAE is not doing perfect reconstruction because of its nature, but if it's trained close enough, you can get something that is supposed to be approximately reconstructing the original. And again, the difference from that video where I was performing the piano is that this is the same input output. It's not trying to kind of take a different corpus. So in a full rate, what we have, this would be the input and this would be the output. And the experiment is really simple. What I've tried to do is basically listen to both of them together and see if they match. And then in the next example, I kind of introduce more noise or less bitrate. Only partial information about the encoding is used to reconstruct the top part, and I listen to them together, try to figure out how many errors or how many false notes you get. And then you can keep on lowering the bitrate, basically, with the amount of information that goes between the encoder and decoder, and see how that reflects on the ability of these two different musical lines to match each other. So kind of it sounds like an accompaniment experiment, but basically it's really kind of just trying to understand the math of variational autoencoders by seeing, taking, the lower part as the encoding and the upper part as the decoding with some kind of a control over the amount of bits or the information that passes between the encoding and decoding, and trying to see, where things start breaking apart. Now, not only that, we can expect that they will break apart, there is some kind of an aspect of saying, well, this, by lowering the rate, maybe this becomes more independent of this, maybe it becomes more creative. So the ability to control the input-output relations in some kind of a tunable way, you can think about this as, like any synthesizer, you want to have some knobs that you can control to generate something that you desire. So here on the creative level, you want to have some kind of a knob that allows you to say, I want, the output to correspond to this extent or lesser extent to the input. So this is the full rate, and you will hear them both playing together. And I think you can hear that, just try to notice if they sound at least kind of harmonious together or not. So. So just explain what's going on here. The piano is the query, the input, and the vibraphone, the more metallic sound is the decoding. I told you the instrument's totally opposite, right? The vibraphone is giving the lower notes, and the piano is kind of improvising on top of this. So I think, here, at least to my musical evaluation, they seem to be playing together relatively in sync and relatively playing the same chords and kind of falling on the same musical logic. Once you start reducing the bit rate, you start having kind of just separate lines. I think you can hear that the piano is kind of struggling, that it cannot find its way. It improvises something that probably, sounds just like as a fake notes, or somebody kind of like looking for his place on the keyboard while somebody is actually playing the song he learned. And of course, if you reduce even more the bit rate, that's what it sounds like. So first of all, the piano is much sparser. You cannot really find a lot of the notes that it's supposed to generate. So sometimes try to hit one or two notes. And just as a really proof of concept that, you can somehow control, your output by controlling basically encoding, decoding with some kind of a handle in the middle. How to do this in a way that actually is musically meaningful is still an open question. But this is kind of the overall idea of trying kind of to combine some of these generative methods with some sort of an input, a query, or a constraint that will generate a meaningful output. Stop it. Okay. So so that's pretty much that's the end of the presentation today. which was really more of kind of that overview and motivation of how these things formally and informally fit into something that is creative. Okay, so I'll stop the share and yeah, see if there are any comments or questions.